Hello, thanks for listening in. It's great to have you with us. In this short video, I'm going to show you an interesting possibility for including dark energy as an operational component to the universe. First, we will develop the theory in the weak field limit and derive a formula for a weak field force law. Then we will revisit the problem of dark energy as a contribution to space-time curvature and general relativity. To understand what we're talking about, suppose that gravitating bodies in the universe are natural emitters of dark energy. For massive bodies with spherical symmetry, like a star, we'll give this radiation three important properties. One, dark power output is proportional to the mass of the gravitating body. Two, dark energy flux radiates isotropically at the speed of light. And three, dark energy flux continuously violates the law of conservation of energy. What I mean by this is that the mass of the gravitating body does not decrease as this energy is radiated. Of course, we're not saying anything about the source of the dark energy or even whether it can be detected. That's all important, but for now, let's just write down some simple freshman physics based on requirements 1, 2, and 3. For a test star of mass m, it's easy to write an associated 1 over r squared dark energy flux. In this formula, the constant alpha, shown by the floating blue arrow, has units of inverse meters and is assumed to be very small. In fact, a rough estimate for alpha suggests a value of around 6 times 10 to the minus 21 inverse meters. A better understanding of alpha follows from a simple flux integral showing that alpha is a measure of the dark power output of the star. For the record, the dark power output of the sun calculates to about 10 to the 35 watts, which is 1 billion times larger than its electromagnetic output. Next, we can write a formula for an associated momentum flux and energy density surrounding the star. These two formulas can be immediately combined to form a null current 4 vector appropriate for a field that moves at light speed. Now let's use this information to calculate a weak field force law similar to Newton's gravitational law. According to the null vector, the energy density of the dark field is positive, so it will have an equivalent mass via E equals mc squared. This means that the effective mass of a star isn't just its conventional mass anymore. Instead, it includes an exterior mass field proportional to r. We can insert this mass field directly into Newton's gravitational law, producing a slightly modified law given by this formula. Based on the value of alpha, it's clear that the local contributions to the field of a star are negligible. On the other hand, at large distances, the additional term generated by the dark field will begin to dominate, and the velocity profile of test particles about the star will go flat. Before extending our theory to strong gravitational fields, it's necessary to discuss the source of the dark field and the weak field limit. First, we extend the definition of the Schwarzschild radius as a complex oscillator. In this equation, the frequency of oscillations is currently unknown. A simple time derivative of the radius becomes the boundary of a vector velocity field propagating longitudinal traveling waves. Next, a scalar field P can be established from the magnitude of the velocity field and functioning as a radiator of outgoing spherical compression waves. These fields can be combined using a familiar classical formula from continuum mechanics to derive the energy flux. In this equation, both the frequency and the pressure constant are unknowns, but we can make a reasonable guess for both. In these formulas, the frequency depends on the square root of alpha and is a very small number. The pressure constant is familiar as it is 2/3 the value of the associated black hole energy density. A graphic illustration of the flux is available from this animation. These waves show similarities with acoustic wave phenomena, except there seems to be no medium for the waves to travel through. In addition, the animation does not show gravitational redshifts, which can only be determined by general relativity. We note, however, the very low frequencies and long wavelengths associated with the radiation. As an example, a period of redshifted oscillation for the sun is about 4 hours. Now comes the hard part. We need to show how this flux of dark energy can be accommodated by general relativity. For this, we'll need to revisit the problem of the Schwarzschild vacuum. This problem assumes a static space-time with spherical symmetry, implying the line element given by this formula. Without the source, the problem is solved by setting the Ricci tensor to 0, leading to components of the metric given by these two formulas. Now let's solve this problem again with a field of dark radiation traveling through the space-time. To do this, we will begin by adding a dark Lagrangian to the Einstein-Hilbert action. This Lagrangian looks very familiar and has a value which is the weak field energy density with a minus sign. The field quantity is the tensor Casim mu nu and is a traveling spherical wave with an argument z star, including the tortoise coordinate r star, which is not known until the field equations are solved. The dark stress tensor shown here follows naturally from Lagrangian mechanics and features only an energy term and a radial pressure term. With an explicit form of the dark source, the field equations for the Schwarzschild vacuum with dark energy flux can be solved, leading to components of the metric determined by these two formulas. We see that the flux of dark energy introduces an almost irrelevant contribution to space-time curvature. For the Sun, this modification is on the order of 10 to the minus 17. That's the solution, but it's a simple exercise to show that dark radiation adds a small positive Ricci scalar curvature to the space-time, falling off like 1 over r squared. This looks like a Gaussian curvature in differential geometry and can be shown to be derived from a bilinear combination of two principal curvatures, k1 and k2, which are traveling spherical waves. Specifically, the scalar curvature is a sum over two independent curvature waves. To reiterate, what we have shown here is that the kinetic flow of the dark field generates a Gaussian-like curvature for the Schwarzschild vacuum. Now suppose we write the formula for the gravitational redshift using the time component of the slightly modified Schwarzschild metric. Using the Schwarzschild radius as the lower limit determines a redshift formula for the frequency of the emitted dark waves. These waves will undergo redshifts of several orders of magnitude as they climb through the gravitational field, rendering a power formula modified by space-time curvature. To summarize, we have shown how energy-violating radiation can be inserted into the Einstein field equations in a natural way without any significant changes to the curvature of space-time. Our theory eliminates the concept of pressureless matter in the universe and shows promise for explaining dark matter halos and a uniform background of dark energy. Thanks again for listening in. We hope you've enjoyed this short video and have a great day.